Hello students, welcome back. We're going to continue today with carbohydrates part 4. But I'm going to do something a little different. I'm going to go back because I need to explain some things to you about isomers. And so there'll be a little digression here, and then once I finish this slide, we'll continue where we left off. Okay, I'm going to draw quite a few molecules here. I'm going to move this to the side. Okay. Okay, I'm going to start out drawing glucose. So CHO. It doesn't matter because that's not chiral. 2, 3, 4, 5, and 6. So all you have to remember for glucose is the OH goes on the 3 OH goes on the left. Two OH. And so this is D-glucose. Now what I'm going to draw for you, I'm going to change just one. Okay, how many chiral centers does D-glucose have? 4 chiral centers. Now what I'm going to do, I'm going to change one chiral center. And the one that I'm going to change is going to be, let's change the 2-carbon. I could change any of them, but I'm just going to change the 2-carbon. So it's going to be CHO. That's 2, 3, 4, 5, and 6.
Okay. When we draw them on the test, do you want us to put the hydrogens on the other side?
Yes, put the hydrogens on the other side. I'm just not drawing them today because I'm just trying to go faster. Okay. Yes. Her question was, Dr. Merida, when we draw this on the test, do we need to put the hydrogens on the other side? Yes, you should. I should also. I should be putting these hydrogens here, but I don't know why I'm lazy today. I shouldn't be.
It's okay. I just wanted to know if I needed to on the
Yes, and so what I'm going to do, I'm going to change. I want to do this just like I have it here. So if you would, I'm going to erase this. I hope none of you wrote with a pen because I'm going to put this on the other side actually. And for those who do have a pen, which it sounds like, I apologize. Okay, and I'm going to put here OH. And so the only one that I'm going to change is going to be the 4 one. And so this is OH. Just trying to follow my notes because my notes kind of make sense to me in my mind. Okay? And so this molecule is just different from glucose in one chiral center. Okay? And this is D-galactose. D-galactose. I'm just going to put D-gal here. I'm going to move it up because I need that space underneath. Okay, I can't go up any higher for some reason. Ooh, hope it doesn't have the hourglass here. I don't know. Okay, there we are. So I'm not going to do that anymore. He doesn't like that. Okay, that's D-galactose. It's different from glucose in just one position. Is that clear to everyone? Only one of those is changed. Let's do another one. Let's change it in two positions. So we're going to make it different from glucose in 2 positions. So we're going to change, on this one, we're going to change 3. Let me see which one we're changing. We're changing 3 and 4. We're going to change 3 and 4. So you should know how to draw that. So I'm going to just change. It's going to be 3 and 4 are going to be different for glucose. CHO, 2, 3, 4, 5, and 6. CH, 2, OH. And so I'm just going to change. Which 2 did I say I would change? 3 and 4. So normally 3 is on the left. So this time we're going to put 3 on the right. And normally 4 is on the right. We're going to put 4 on the left. Okay. And so everything else is going to be on the right. Okay? And this aldose has a strange name. It's called glucose. Glucose. And it's different from glucose in how many positions? 2. So we have glucose, and then we have galactose that's different in 1 position, and then we have glucose that's different in 2 positions. What do you think I'm going to draw for you next? Something with 3 positions. And what we're going to change, so you'll know, we're going to change 2, 3, and 4. We're going to change 2, 3, and 4. So here we go. You know how to draw it already. Four, 5, and 6. Okay, I'm going to change 2, 3, and 4. So this is going to be OH. That's 2. OH. That's 3. And OH. That's 4. And so this is going to be OH. Oh, glucose. Let's go back to that third one, glucose. Is that D-glucose or L-glucose? Why do you say it's D? Who said D? Exactly, that 5th chiral center is on the right. Exactly, that's D-glucose. And so this next compound that differs in 3 chiral centers is going to be mannose, D-mannose. D-mannose.
Are these all found in the body?
Yes, well, I don't know about glucose. Glucose probably is not. But mannose is, galactose is, and glucose. All of those are. Now, we've changed glucose in 1 position, 2 positions, 3 positions. Now what are we going to do? What do you think I'm going to do next? I'm going to change all of the chiral positions. What is this molecule going to be called? Wow. L-glucose. Exactly. Exactly. So we're going to change all of them. CHO, 2, 3, 4, 5, 6. CH2OH. And so we're going to change every one of them. So glucose is right, left, right, right. So it's D-glucose. L-glucose is going to be left, right, left, left. And so what's the name of this molecule? L-glucose. Now I'm going to draw another molecule where, see, all of these have the same chiral centers. I'm going to draw another molecule that has the same number of atoms of all of these, but it doesn't have the chiral centers aren't there. So CH2OH, C double bond O. Four, 5, and 6. Okay? Now, on this molecule, the carbonyl carbon is on carbon 2 and not carbon 1. What's the name of this molecule? Come on, you all. It's a it's a ketose. The carbonyl it looks just like glucose, but the carbonyl is on carbon number 2 instead of carbon 1. What's the name of this molecule? Fructose. Exactly. This is fructose. Is this D-fructose or L-fructose? D, exactly. Okay. Now I'm going to explain to you why we've done all of this. All of these molecules, because they all have the same number of, they all have 6 carbons, 12 hydrogens, and 6 oxygens, they are all structural isomers of one another. So all of these are structural isomers. All of them are structural isomers. All of these molecules are structural isomers of one another. All of them. Because they all have 6 carbons, 12 hydrogens, and 6 oxygens. Is everyone okay with that? Now, for these first 5 molecules, they all have the same chiral, they all have the same chiral centers. The chiral centers aren't the same, but they all have, all of the chiral centers don't all have the same configuration, but all of them have carbons 1 through 4 are chiral centers. And so all of these molecules are called stereoisomers. All of these are stereoisomers except for which one? Which one is not a stereoisomer? Fructose is not. So we can go from here to here. All of these are stereoisomers. Everyone with me so far? Let me know if it doesn't make sense. So D-glucose, D-galactose, D-gulose, D-mannose, and L-glucose, they are all structural, they're all stereoisomers. Are they structural isomers? Yes, they are structural isomers, but they're also stereoisomers. Okay. Let's do something else here. This one is kind of hard to do, so I'm going to have to. Let's go to the. Let's do this one first. Let's do this one first. D-glucose and D-galactose only differ in one position. They're almost the same, but they only differ in the configuration of one of their carbons. So these two are called epimers of one another. Epimers. They are stereoisomers that are epimers. I shouldn't have done epimers yet. I should have done something else before epimers. Has anyone written that with a pen? Okay. That's okay. Go ahead. Go ahead. Now okay, let's do this one. All of the molecules that have differing chiral centers, that have the same chiral centers, their configurations are different, but they're not mirror images. So D-glucose, D-galactose, D-gulose, and D-mannose, they have the same numbered chiral centers, but they're not mirror images. These are called diastereomers. Yes, the first 4 are called diastereomers because they differ in the configuration of their chiral centers, but they're not mirror images. But they're not mirror images. Now, a specific diastereomer, where it only differs in one carbon's configuration, is called an epimer. So, galactose is a 4 epimer of glucose because they differ at position 4. Does that make sense? Galactose is a 4 epimer of glucose because it only differs in carbon 4.
So you number it by whatever carbon it is?
Yes, the epimer, exactly. Glucose and galactose are epimers, and galactose is a 4 epimer of glucose. What epimer of galactose is glucose?
No, 3.
Where do they differ?
3.
So galactose and glucose differ at 3?
Oh, I can see galactose.
Galactose,
Oh, and I was looking at the other. So they did before.
It's 4, exactly. So glucose is a 4 epimer of galactose, and galactose is a 4 epimer of glucose. Okay. Question. A diastereomer are going to be isomers, stereoisomers, that differ from one another in their configuration of their chiral centers, but are not mirror images. They are not mirror images.
So glucose would be a 3 epimer of galactose.
Exactly.
That's what I was looking
Exactly. You're correct. Her question was, so glucose would be a 3 epimer of galactose, and that is correct. That is correct. What about mannose? Is mannose an epimer of glucose? Of glucose? Anyone? Is mannose an epimer of glucose?
No, 'cause it's more.
Exactly. It's more than one position. Exactly. Very good. Very good. Now, the last definition, the last term. If all of your chiral centers are different, and you have the perfect mirror image, you're not called a diastereomer. You're not called an epimer. Does anyone remember what you're called if all of your chiral centers are different? Enantiomer, exactly. And so L-glucose is an enantiomer of glucose. So enantiomer, E-N-A-N-T-I-O-M-E-R. If all of your chiral centers are different, and that molecule is a mirror image, one is a mirror image of the other, just like L and D, they're called enantiomers. Under L-glucose. L-glucose is an enantiomer of D-glucose. It's a stereoisomer, but it's not a diastereomer. Exactly. All enantiomers are mirror images. All enantiomers are mirror image. His question was, so all enantiomers are mirror image? And my answer was yes. Okay. And that's what I wanted to make sure you understood about isomers. There are structural isomers that have the same number of atoms of everything, but they don't stereoisomers unless those chiral centers have the same numbers, but different configurations. Does that make sense to everyone? Is that confusing? Did the lab yesterday, did the lab help you to understand what Fisher projection means? Very good, very good, very good. Okay? So I'm finished with, that's all I want to say about isomers now. And now I want to continue with where we left off last time. If everyone is okay with that. Let me see where we left off. Okay, this is where we were. Okay, we drew glucose yesterday. We were just looking at the difference between glucose and fructose. They're like brother and sisters. Now, glucose and fructose, are these stereoisomers? Are glucose and fructose stereoisomers? Yes. Everyone agree? That makes them structural isomers. I'm asking, are they stereoisomers? Let's look and see. Here we have glucose. Here we have fructose. They are structural isomers because they have the same number of carbons, hydrogen, oxygen. But they're not stereoisomers because glucose has, the chiral centers for glucose are 2, 3, and 4. The chiral centers for fructose are just, the chiral centers for glucose are 2, 3, 4, and 5. The chiral centers for fructose are 3, 4, and 5. So they're not stereoisomers. They're only structural isomers. That makes sense, everyone? It's a big concept there. Okay?
You have to have the same number of classes?
Yeah, the same numbered chiral centers. Like if 2, 3, like glucose and galactose are stereoisomers because the chiral centers in glucose are 2, 3, 4, 5. The chiral centers in galactose are 2, 3, 4, and 5. But they have to also be structural isomers too, though. And the same constituents on all of them. So, but let's not get into all of that. Okay. So let's see where we left off last. Okay, we have glucose and then we had fructose. And what I was about to show you is how to close the ring of this ketose to make a hemiketal, to close that glucose ring. Everybody remember that? So let us do that now. So I'm going to redraw fructose. So let's redraw fructose here. You all ought to get tired of drawing. CHO 2, 3, 4, 5, and 6. CH2OH. And what I'm going to do here, so those chiral centers are the same. OH, OH. And I'm going to make this one red because this is the one we're going to use, OH. And so this is D-fructose. Oh, right. Oh, thank you. Exactly. This is not an aldehyde at the top now. Very good. This is CH2OH. It's just an alcohol on top. And so this is D-fructose. How many chiral centers does D-fructose have? 3. Exactly. 3. And so we're going to actually number these carbons. 1, 2, 3, 4, 5, and 6. And now we're going to close this ring. And so currently we have, I'm going to shade the ketone. This is the ketone shaded with the yellow, and our alcohol functional group is shaded with the green. So what's going to happen, this is going to close to the back. We're going to still use the 5-hydroxyl. And it's going to go back here and attack the carbonyl, and we're going to make the ring of fructose. Okay. Now before I do that, since we did the Haworth projection yesterday, I'm going to draw the straight chain as a Haworth projection right before I close it. Okay. So I'm going to have, this will be carbon 1. You may want to watch me draw it first. Carbon 2, carbon 3, carbon 4, and carbon 5. Oh, I'm sorry. I did that wrong. I guess I don't have to erase that. So that's going to be carbon 1. This is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. And this is going to be our red oxygen here with its H. I'm drawing this in a Haworth projection before I close the ring, so you'll see what it looks like before. So this is CH2OH. I'm going to number these CH2OH. Okay. And I'm going to number these carbons. This is 1, 2, 3, 4, 5, and 6. Kind of want you to see it before I close it. Okay. So this is going to go down, OH. This is going to go up. Here's our carbonyl. I'm not putting my H's, but maybe I should put my H's so you'll know. This is an H here, an H here, and H here. Again, this is still D-fructose, but I'm drawing it in the Hayworth projection right before we close it. Right before we close it. So I guess I should put here D-fructose. This. Ooh, no. I don't think I can do this. It's not going to let me do this. Okay, yes. But I didn't get everything. I may not be able to do this. It's not going to let me do it. Okay, I'm going to have to just grab everything and group it. So I need to make this smaller. So I can move this up. Okay, and now what's going to happen next? The electrons here are going to attack this carbonyl oxygen, this carbonyl carbon, and that's going to close the ring. And this hydrogen basically is going to be left to itself. It's going to be released. And so this hydrogen is going to come around and going to attach here with that O. And so now let's close the ring. CH2OH. COH, it's carbon 2, carbon 1, 2, 3, 4, 5, and 6, CH2OH. We're going to have our ring oxygen there. This is going to go down, OH. This is going to be up, OH. And everything else is just an H. And this is kind of D-fructose, but we're going to give it a different name once everyone is caught up with me there. Does everyone see what we did to close the ring? The electrons from the alcohol group just attacked the carbonyl, and it formed a bond there. And so the carbonyl loses its double bond, and now it just makes an alcohol. No, in lab yesterday we did the aldose, we did glucose, and we closed the ring for glucose. But it works the same exact way. I mean, the mechanism is exactly the same. The only thing that's different is that when you have an aldose, you create a hemiacetal. When you start with a ketose, you produce a hemiketal. Exactly. That's the only difference. And so the closed ring structure of fructose here is a hemiketal. And so this functional group is a hemiketal. And this is still fructose. This is still, well, it's still D-fructose, but there are some things about it that are different. Now, is this D-fructose, is it in the pyran form, or is it in the furan form? Furan. Why do you say it's furan? Okay, you can think about it like that. That is right. It has 4 carbons in the ring. But just always think furan has 5 members in its ring. F furan 5. furan 5, and the pyran has 6 members in its ring. 6, P-S-I-X, because it starts with a P2. No, that's not true. But so just remember, furan has 5. Okay, and so this is a furan. Now, is this the anomeric carbon? So let me ask you all a question. This carbon here, this carbonyl carbon, is this carbon chiral or achiral? Achiral, because it only has 3 things. So it has to be, so this carbon is achiral. Now, here, there's that same carbon. Is it chiral or achiral? It's chiral now. So it went from being achiral and it became chiral. And we give a special name to that carbon because it can change. It can change from achirality to chirality. We call this carbon the anomeric carbon. That one carbon, the one that has the carbonyl on it, is called the anomeric carbon because it went from being achiral to becoming chiral. That's the anomeric carbon. Now, this anomeric carbon can have 2 configurations. The OH can be either up or the OH can be down. Now the question for you, for this anomeric carbon in fructose, I'm going to shade it yellow here. This anomeric carbon, do we have it up or down? We have it down. Now, down can be either alpha or beta. So which one? Well, only one of them is down. Down is one of those. So which one is down? Is down alpha or is down beta? Down is alpha because alpha is always less than beta. Alpha is less than beta. And so this is the anomeric carbon here is alpha. And so when you name this compound, you can say, well, this is D-fructose in the furan form with an with the anomeric carbon in the alpha configuration. But that's kind of a long name. So scientists have come up with this name for this compound. We call this compound alpha D fructofuranose. Alpha D fructofuranose. Alpha D fructofuranose. Did I give you the name of glucose before? Maybe I didn't. Now what I'm going to do for just a second, I'm going to go back to the glucose we drew the last time we met. And I'm going to see if one of you can give me the proper name for this glucose. So I'm going to go back. Now here is D-glucose that we drew last time. It is a hemiketal, a hemiacetal. So I'm going to put my H's here so you'll know where the H's are. So this D-glucose, is it in the puran form or the furan form? It's a puran. So I'm going to put it here, puran. I don't know what I'm going to put. I don't have room anywhere. It's in the puran form. Okay. The alpha carbon or the anomeric carbon. This anomeric carbon, is it in the alpha position or the beta position? Alpha. It's in the alpha position. Okay. So it's D-glucose. It's in the puran form. No, not puran. Pyran. It's in the pyrene form, and the anomeric carbon is alpha. Okay, I'm going to go back here. Somebody's going to figure out how to name this. Let's go back to fructose. Here's D-fructose. It's in the furan form. The anomeric carbon is alpha, so we called it alpha D-fructofuranose. I'm going to go back to glucose. We're going to look at it. It's D-glucose. It's in the pyrene form, and the anomeric carbon is in the alpha position. Someone is going to be able to figure out how to name this. I'm going to give you all 3 seconds to think about it. 1, 2, 3. Has anyone figured out how to name this? Yes. Okay, we're going to go with Chapman. Okay, alpha D fructopyranose. Now, but that would be right, but we have glucose here. Okay, let's go here with Kennedy. Alpha D glucopyranose, and that is correct. Simple. Make sense? So this is alpha D glucopyranose. Alpha D. Oh, I just put pyranose. And we call it pyran because it looks like we call it a pyranose because it looks like pyran. Does that make sense? Excellent. Rivers, make sense? Excellent, excellent. Now, let's do a little review here. And let's see what we talked about today. So let's just go over what we discussed today. So here we have fructose, D-fructose. Is D-fructose, is it a stereoisomer of D-glucose? Is D-fructose a stereoisomer of D-glucose? No, it's not. What type of isomer is it? It's a structural isomer because it doesn't have the same chiral center. So what we're going to do here, here we have a ketone functional group and we have an alcohol functional group. There's going to be a nucleophilic attack of these electrons on the number 5 hydroxyl on that carbonyl. And so now we've drawn fructose now in the Haworth projection, and you can more easily see these electrons can attack that carbonyl, open that carbonyl up. This carbonyl carbon is achiral, but then it becomes chiral once that new bond forms. And so we call this the anomeric carbon. And the anomeric carbon can have the OH in the alpha position down or in the beta position up. And so this is a hemiketal that we formed. And so this is still D-fructose. It has it's a 5-membered ring, so we call it a furan. And the anomeric carbon has the OH down, so it's alpha. And so the name of this compound is alpha D-fructofuranose. Everyone okay with that? Lots of information. We spent lots of time today on one reaction, one thing. But that's okay. No, we went over isomers first. That's okay. Thanks. Okay, close your notes. I want to ask you one question, and then we're going to leave. One isomeric question. Okay, I won't go to it. I'll just ask you. This is the question. Okay. No, I'm not going to do that. Okay, this is the question. You have 2 carbohydrates. They differ from one another in their configurations differ. Their stereo configurations differ at only 1 carbon. Let's say it's a 6-carbon carbohydrate. Their stereo configurations differ in 1 chiral center. What is the name that we give to such isomers? We have a different answer. The answer is epimers. Have a great day, you all. Have a great day.